Hi everybody, thank you for coming to watch this Canyon Academy physics video. In this physics 112 concept video, we are going to cover the second half of the week 11 concepts, which include X-ray production, the Compton effect, and de Broglie wavelengths. So the first thing we're going to talk about is X-ray production, and the X-rays that we're going to focus on are Bremsstrahlung X-rays. And so these differ slightly from the characteristic X-rays, which you can look up if you want. But basically, the Bremsstrahlung is a German word meaning breaking radiation. And these X-rays are produced when high-speed electrons are slowed down in a material. And so this slowing down of electrons releases energy in the form of an X-ray photon. And so this diagram below, it's kind of crudely drawn, but it's supposed to represent a cathode ray tube. And so a cathode ray tube consists of a vacuum tube and a charged cathode that fires electrons towards a charged anode made out of tungsten material or copper material most commonly. And so when these electrons are fired in the tube towards the charged anode, it creates an electric current that is known as the beam. And this electric current is powered by a high voltage source, as you can see. And so when these electrons come into contact with the charged anode atoms, I'm going to zoom in on this diagram below, you can see that the electrons are going to change course. And that's because these electrons, like I said, are slowed down in the material, and that's what causes the production of the X-ray. But the electrons are decelerated because this negatively charged electron is going to pass by the positively charged nucleus, which elicits an electrostatic force on the electron. And so this electron is going to be drawn towards the nucleus, and thus it's going to change direction. And so when it changes direction, it actually loses a little bit of the energy that it possessed when it was fired towards the atom. And so this loss in energy is going to result in, and this change in direction is going to result in the production of an X-ray. And so we're going to add some numbers to it over here in the same diagram. But as you can see, these electrons are fired with a certain amount of energy towards the atom. And so we're just going to pretend that this is 80 kilo electron volts. And so when this projectile electron comes into interact with the atom, like I said before, it's going to change direction once it passes by the nucleus. And so so in this case, it lost 60 kilo electron volts. And so the scattered electron is going to leave the atom with 20 kilo electron volts. And so the X-ray that is produced has an energy of 60 kilo electron volts. And so what's important to note here is that the closer the electron comes to the nucleus, the greater the energy of the X-ray photon. And that's because there's a larger disparity between the projectile electron's energy and the scattered electron. So if you were to have the same amount of energy of an electron interact with this atom, but imagine it interacted further away from this nucleus, it's still going to change direction, but the scattered electron is going to have more energy than this 20 kilo electron volts. So that means that this X-ray will actually have less energy. And so this is basically how Bremsstrahlung X-rays are formed. And so the next thing that I want to talk about briefly is X-ray diffraction. And just quite simply, if you remember the Young's double slit experiment, where constructive and destructive interference occurred with waves to produce vertical lines in a diffraction grating, X-ray diffraction is kind of similar in that regard. But in this case, X-ray diffraction occurs because X-rays, as we know, are high energy electromagnetic radiation waves. So these X-rays have small wavelengths, and these wavelengths are actually small enough to where they're in the range of the distances between crystals and molecules. And so X-rays are capable of creating a diffraction pattern that results in a 2D image, as you can see below. And so the next thing that we're going to talk about is the Compton effect. And both the Compton effect and the de Broglie wavelength have a sort of a concept that's sort of insignificant because the Compton effect can only be observed for X-rays. But both of these concepts, the Compton effect and the de Broglie wavelength, provide evidence for the particle nature of light, because we know that light can exist as both a particle and a wave. So the Compton effect is basically the result of a high energy photon colliding with an electron. So what we have here in this diagram is we have a photon with an initial wavelength, and once it interacts with this electron, the electron is going to recoil as the photon is scattered away, and the electron recoils basically because of the law of conservation of momentum. And so what's important to note here for the Compton effect is that you know that the larger the angle that the electron has, or I'm sorry, not the electron, that the wavelength, or that the photon has scattered, the larger the wavelength of this initial photon. And so the equation is illustrated below, where you can see that the incident wavelength is subtracted by the initial wavelength, and this is equal to Planck's constant over the mass of the electron times the speed of light, multiplied by 1 minus cosine of the angle. So you can see how you can calculate the wavelength that is going to result from the scattered photon. And so, like I said before, the Compton effect is only observed for X-rays because these wavelengths are so small. And so lastly, we're just going to talk about the de Broglie wavelength shortly. And Louis de Broglie just basically figured that because light acts as both a wave and a particle, particles should therefore have wave properties. And he derived an equation for the wavelength of a particle that's moving, and that equation is wavelength is equal to Planck's constant over momentum p. And momentum p is just equal to the mass of the particle times the speed of the particle. So this is basically all of everything that you need to know for X-ray production, the Compton effect, and de Broglie wavelength. So if you have any questions, feel free to leave them in the comments below.